Hello, my name is Giselle Cruz Chamorro. I would like to give you a brief presentation of this poster entitled Development of a Polycaprolactone-based composite reinforced with graphene nanoplates and anthocyanins produced using 4D printing. In 2020, the World Health Organization estimated that every year 600 million people in the world get sick from contaminated food and 420,000 die from the same cause. Pasteurization of milk has reduced the number of illnesses. However, there are still cases of infections associated with pasteurized milk. Controlling the quality of foodstuffs and, in particular, milk, is fundamental to maintaining food safety and human health. The research focuses on exploring the potential of 4D printing by developing a composite material, which includes a polycaprolactone matrix, a graphene nanoplatelet reformants, and glucuronthocyanins as an additive. The objective is to provide real-time information of the freshness and safety of milk. A total of 5 formulations were made to observe their behavior once printed, each one containing different materials and different concentrations, as shown in Table 1. Exploited graphite was provided by Tecnológico de Tierra Blanca. The exfoliation of the graphite was performed with the help of a Cole Palmer ultrasound tip at 50 Hz for 80 minutes. The pelletized polycaprolactone was processed in a coffee knife mill until it was obtained in the small spheres and powdered. The formulations containing 0.2% carbon were introduced in a mixer for 30 minutes. Glucuronthocyanin was extracted at the facilities of the Universidad Autónoma de Chihuahua by Dr. Johan Mendoza Chacon using the high-intensity pulse electric field method. Anthocyanin were diluted in 96% ethyl alcohol. Formulations containing anthocyanins were placed in a measurement oven at 40 degrees Celsius for 24 hours. Filaments were produced corresponding to the 5 formulations described in Table 1. The temperature of the fillable extruder was set at 80 degrees Celsius. The specimens were printed using a quality printer, for which 2 types of specimens were created, mechanical and permeability. The anthocyanin solution was characterized using a UV spectrophotometer. Likewise, the anthocyanin solution, the polycaprolactone, as well as the proposed filaments, were characterized in FTIR spectrophotometer. A water vapor permeability test was performed in permeability cells, following the methodology proposed by the ASTM E96 standard. Finally, mechanical tension tests were carried out according to ASTM D638. In Figure 6, the band in the region between 200 and 300 nanometers implies a p-bond to p antibond transitions due to carbon-oxygen and carbon-carbon groups, suggesting its identity with cyanidine triglucoside. Figure 7 shows the comparison of polycaprolactone with anthocyanins and ethyl alcohol. In the spectrum related to polycaprolactone, we observe the characteristic bands of polycaprolactone found at 2950 for the asymmetrical stretching of carbon-hydrogen, at 2860 for the symmetric stretching of carbon-hydrogen, at 1722 related to the stretching of carbon-oxygen group, at 1245 for the asymmetric stretching of carbon-oxygen-carbon, and finally at 1160 for the symmetric stretching of carbon-oxygen-carbon. The spectrum of anthocyanin shows a peak at 3320, corresponding to oxygen-hydrogen stretching in alcohols. In addition, the peak at 2970 is mainly related to the stretching of carbon-hydrogen bonds. The peak at 1045 is associated with the stretching of carbon-oxygen-carbon bonds. Figure 8 shows the filament spectrum of polycaprolactone in combination with nanoplatelets and anthocyanins. These results suggest that the main absorption bands correspond to polycaprolactam, with the absence of new peaks related to anthocyanin or nanoplatelets. Therefore, it can be stated with certainty that there is no chemical interaction, but only a physical interaction between the materials. Figure now 9 shows the result of the permeability test, where it is observed that the polycaprolactam and anthocyanin formulation specimens are the most permeable, while the polycaprolactam and anthocyanin and nanoplatelets specimens are more impermeable. This is due to the fact that the addition of anthocyanins increases the intermolecular interactions between the polymetric matrix and the additive through non-covalent bonds, which makes it difficult for moisture to pass through. In addition, nanoplatelets are considered impermeable fillers for small molecules. Tortuosity increases with the presence of nanoplatelets in the matrix. In the evaluation of the results, it is confirmed that filaments can be obtained by blending without generation modifications in the chemical structure of the matrix. These findings support the feasibility of combining nanoplatelets as a reformant and anthocyanins as an additive in a polycaprolactam matrix. In addition, UVB's analysis suggests that anthocyanins may be pH related, evidenced by the absence of a band in the visible spectrum, unlike that found in other anthocyanin monomers. The method used to produce filaments is viable, since no signs of deterioration in the materials, such as anthocyanin decomposition, are detected. As for the permeability test, it was shown that the most impermeable material is the one with the polycaprolactam, anthocyanins, and nanoplatelets formulation, due to the reduction in pore size. Therefore, the addition of nanoplatelets was beneficial in improving the impermeability of the material. We would like to thank Juan Carlos Méndez Méndez for his assistance in the development of formulations and filaments, and thank the Instituto Tecnológico de Querétaro for the scholarship granted to the students for the realization of this project, as well as the facilities provided.